because like not only it's a really fundamentally new phase of matter, but it's also like it has real-world applications. So superconductors are behind some of the most cutting-edge technologies, like for example levitating trains we have today, and that are the fastest trains we currently have on Earth. So let me explain what I mean with the quantum phase of matter. So we all know different phases of matter on the example of water, right? Water can be liquid. If we cool it down, it can freeze, so it becomes a solid. If we heat it up, it can be in its gas form. And these is what we call different phases of matter. And there are not only 3 phases of matter, but in fact there are many more. Like even water can exist in more phases of matter, so it turns out it can not only freeze into one particular like solid form, but there are different lattice geometries, and all these like different geometries correspond to different kind of ices water can freeze into. So what do we need to have in order to have a phase of matter? Well, first of all, we have to have many particles. So we're leaving the single particle limit here and see what happens when we put together more and more particles. And also very often we have interactions between them. Okay. So even water consists of water molecules that are quantum objects, right, that obey quantum rules. The phases of matter here are actually classical. So they are well described by classical physics. So this raises the question basically if there are also new quantum phases of matter, where like really quantum mechanics gives rise to these phases of matter, and you see like the quantum mechanics on a macroscopic scale, so to say. And the answer is yes, of course, otherwise there would be no lecture. An example here is superconductivity. So you can see a little superconductor here levitating. So what are we going to do in this lecture? So first of all, First of all, I'm spoiling my talk here. So we will learn about what is superconductivity. We will also have live experiments, as the Saint said already. And then we will learn about some real-world impact of superconductors on the example of these levitating trains. And then finally, we will also quickly touch upon some theoretical understanding. How can we understand these superconductors? Okay. So when superconductivity was discovered, it was actually like a super big surprise. Nobody really expected it. And the features you saw, like the properties these superconductors had, were unexpected and to some point even counterintuitive. So in order to understand this a little bit better, let us go to an example we all know, which are watermills. So here, what you can see is a watermill. We have a river that flows, and this flowing water can actually cause this wheel to turn. And the wheel then is connected to some shaft, which itself is connected to some gears, maybe that can be used to grind grain, right? So the energy here provided by the flowing water can be used to turn the mill stems. And this thing will operate as long as the river is flowing. But can we actually also have such a watermill without brook? Well, there were many different like design ideas or suggestions of having such a small river in a small like closed space. And this is one of them, for example. So you can see we have this vessel, gravity pulls down water. Here we have a big cross section, so this means we have a big pressure, therefore big force. Here the small cross section is much smaller, meaning small pressure, small force. And of course, if we just like leave this thing, what would happen is the opposite way actually, right? The water would flow back until it balances out and the water level is equal here on both sides. But what now if I give some impetus to the water? Can actually the impetus of flowing water keep this water moving? And then we could even insert like a little wheel here and extract some energy out of this. Well, this is not working, right? Right? Experience tells us this. No, this will not happen because of friction. And actually for centuries, scientists or even maybe investigators or whatever, they try to come up with like new design ideas of what is called like the perpetual motion machine. And even famous people contributed to this, like Leonardo da Vinci, the guy who also painted the Mona Lisa. Well, it doesn't work. And the reason for this is a famous law we have in physics, which is the law of energy conservation. So it basically states that energy cannot be created or destroyed, but it can only be transformed from one form to the other. So in every closed system, the energy is conserved, can only changes its form. So here what happens is that the initial kinetic energy is either transformed or converted into heat through the friction we have here, or it's extracted and released as work. So the fluid we will talk today is not water, but it's actually some electron fluid that exists within metals or wires. But the picture you can have in mind is very similar to the flowing water. So also an electric current needs a driving force, and this driving force is voltage. And there's a famous law, Ohm's law, that says that the voltage is proportional to the current, and the proportionality constant here is the resistance. So this is basically the friction we have for these electron fluid. Right. So where is this friction actually coming from? In order to understand that, let us quickly recap. We just learned that atoms consists of nucleus, actually the protons and neutrons, and then some electrons surrounding the nucleus. And in almost all of the solids we have, these atoms form some periodic lattice here. Okay, so this is a simple cubic lattice. You can see we have an atom sitting in every corner of this cubic lattice. There are also different lattice geometries. And in a metal then, actually not all of these electrons are like bound to these positions, but some of them, which are called conductance electrons, they can freely move around the lattice. And it actually turns out that they can really freely move around the lattice. So imagine that this is like a perfectly periodic lattice, then the electrons would not feel any friction coming from the lattice. But the friction is coming from two different sources, which are first of all lattice vibrations. So think of these atoms, they don't sit perfectly in place, but they can just like wiggle around a bit around their equilibrium position, and this gives rise to these lattice vibrations. So you can basically think of them as some kind of viscous medium for the electrons, which will give rise to friction for the electrons and therefore resistance. And the other source of friction are lattice defects. So these lattices usually are not perfect. So what can happen is that an atom that is supposed to sit here is missing, or it's like you can find it in a different position where it's not supposed to be, or also like an atom of a different or wrong element is like replaces the original atom here. And this is actually really, really common. So imagine you want to buy a piece of copper and you want to get like ultra pure copper. Then what you would get is usually copper which is 99.9999% pure. So there's 6 nines involved. Okay? So this seems pretty pure. So only 1 out of 1,000,000 atoms is an atom of the wrong species. But if you think now, like, if we have like a 3D material, 1,000,000 atoms actually contained in a cube consisting of 100 times 100 times 100 atoms. And like, if you imagine how big this actually is, this is on the scale of nanometers. So if you have an actual piece of copper, you can imagine there you already have a lot of these lattice defects, even though it's really, really pure. Okay, so the energy we lose, or use this friction, or actually we learned we will not use it, but it will be converted into heat. And it turns out that the number of these lattice vibrations here depends on the temperature. So if we cool down the sample, the number of lattice vibrations should decrease. And this also means that the resistance will decrease with decreasing temperature. Okay. So what happens now if we cool down our metal really by a lot, close to absolute zero? And at that point, it was an open question. It was really not clear. And there are different things you can imagine, right? So the first of which is that electrons basically freeze. So we thought about electrons as some kind of electron fluid. And similar to water, you can think of like if you just cool it down, they would freeze and become immobile, which would actually lead to some infinite resistance. The second option is that the resistance would become constant at some point, because we still have these lattice defects, right? The lattice vibrations, they decrease with decreasing temperature, but the rest resistance is then given by the lattice defects. Or the third option was that the friction disappears discontinuously and goes to zero. So in 1911, there was a groundbreaking experiment by this gentleman here, Heike Kamerlingh-Onnes, who was a Dutch physicist. And he was basically specialized, or his research was about liquefying gases. So for example, he was the first one to liquefy air. Then at some point he liquefied oxygen, I think, which has a critical temperature of around 90 Kelvin. He liquefied nitrogen. This is what we also have here, which has a critical temperature of a little bit below 80 Kelvin. And then in 1908, he was the first one who actually could liquefy helium. And liquid helium is really, really cold. It has a critical temperature of around 4 Kelvin. And at that point, it was really the coldest temperature they had on Earth. And I think he even managed to cool it down more by reducing the pressure. Okay, so then in 1911, there was a groundbreaking experiment by him where he immersed mercury, like solid mercury, into liquid helium. And this is his lab, this is Kamerlingh-Onnes, this is the lab technician, and this is where they did this experiment. So what did they find? What you can see here is a resistance curve. This should be resistance. You can see it's measured in ohm, yeah, as a function of temperature. And what happens first is that the resistance decreases continuously, and then suddenly it drops. And it drops to like a very, very small value, basically too small to measure it. But you see this drop is really, really sharp. And that was something which was really not expected by nobody. And Kamerlingh-Onnes also immediately realized the significance of this finding. And he was saying that mercury has passed into a new state, which on account of its extraordinary electrical properties may be called a superconductive state. And superconductive because there's really zero resistance.
Another point here is, if you look at that graph, up until about 50, 60 years ago, this is how we make graphs. 400 degrees, 410 degrees, 420 degrees.
Oh yeah, this axis is a little bit off, yeah. Right, and his finding also recognized, like he obtained widespread recognition for this finding, including the Nobel Prize 2 years later.
Is there a reason he chose mercury?
I think he chose mercury because you can distill it very well,
Okay.
which means you can make it very pure.
Okay.
Actually, it turns out that almost all metals have this behavior. But still, it took almost 50 years to really understand this and to get a working theory that describes this superconductivity. So here let me show you some, or actually the currently known superconductors, because this of course sparked like a lot of research in this direction. And as a function of the year of discovery, and as a function of the critical temperature. So here the first one that was discovered was mercury. And then you can see also other elements were tested, like lead and niobium. And up to the late 1980s, like this niobium Gemini was the known superconductor with the highest critical temperature of around 27 Kelvin. And then in the late 1980s, there was actually a big breakthrough because this new class of superconductors was discovered here, these ceramics. And these ceramics have a much, much higher critical temperature. So they become superconducting at much higher temperatures. And really note the change in axis or in scale here, right? Here 1 unit is 10 Kelvin. Here 1 unit is 50 Kelvin. So actually, this is pretty cool because we do not need liquid helium, which is pretty rare and pretty expensive to cool the samples anymore, but liquid nitrogen is enough. So the superconductor we will work with today is this YBCO, and we can use liquid nitrogen to make it superconducting. Oh yeah, in terms of like Fahrenheit, which you might be more familiar with, this is minus 320 Fahrenheit. I, as a German, absolutely. Okay. Right. And basically, like all these superconductors up here, we would call them high temperature superconductors. You can see, like, there's even more trend in the search of like superconductors with higher and higher critical temperature. Hydrogen sulfide here is, I think there's even a newer one, which was like with a higher critical temperature. This was discovered in 2015. But you can see this only becomes superconducting at like enormous pressures, like 150 gigapascal. But the critical temperature is pretty high, so if you go to Antarctica, you can make this thing superconducting even without cooling it down. Right, so a superconductor is basically 2 main features. One of them we learned about already. It's the zero electrical resistivity below critical temperature. And the second one is the so-called Meissner-Ochsenfeld effect. So the Meissner-Ochsenfeld effect means that an externally applied magnetic field is fully repelled from the inside of the superconductor. So you can see this here. This is above the critical temperature. So the magnetic field can penetrate the material. And if you cool it down and make it superconducting, then the external magnetic field gets expelled. And the inside of the superconductor is basically field-free. Why is that so? Because superconductors are perfect diamagnets. If you don't know what a diamagnet is, they basically weaken the external magnetic field because their magnetization is oriented exactly opposite to the magnetic field, to the external magnetic field. And perfect means that it has the same magnitude as the external field. So it really cancels out the external field completely. And this is done because the superconductor basically sets up electric currents near its surface, which expel the magnetic field. Okay, so the result of this Meissner-Ochsenfeld effect is, first of all, we don't have a magnetic field inside the superconductor. Secondly, also the external magnetic field is somehow modified because the external field, or the total field, is now given by a superposition between external and internal field. And so you can basically see that the field lines get banded around the superconductor. And maybe the coolest result is that superconductors can levitate above magnets because of that. So if we put a magnet here that creates this external magnetic field, the superconductor would levitate above it. And we will see this very soon. Yes. So these types of superconductors are called type 1 superconductors. They have two phases, like the metallic phase and then the so-called Meissner phase. There are also type 2 superconductors, which have a third phase, the so-called vortex phase. So you can see here in these type 2 superconductors, the magnetic field can actually penetrate the superconductor through these vortices. So we can enter this phase when we have a finite magnetic field. Right, I mean, you can call such a vortex also a flux tube. You can see it here maybe a little bit better. These flux tubes are regions that are normally conducting and where the external magnetic field is concentrated in. And the rest of the material is still superconducting. Okay. And basically all of the high TC superconductors, including the YBCO sample we have today, are like these so-called type 2 superconductors, so the superconductors with a vortex phase. So this vortex phase gives rise to some other cool phenomenon, which is called quantum locking. So when we put such a type 2 superconductor above a magnet, it gets locked in position. And the reason for this is that we have these vortices, and these vortices are usually not free, but they are pinned at some lattice defects. And if we now try to move our superconductor through some inhomogeneous magnetic field, this would, so the external field would change, and this would, via magnetic induction, create some electric potential. And this electric potential would want the currents outside these vortices to move. But they cannot, right? Because they're pinned. And so this basically gives rise to this quantum locking. But we only see it if we put our superconductor on top or in an inhomogeneous field. Like in a homogeneous field, we could still move our superconductor. And this is something we will demonstrate now, or Ruben will demonstrate now. So this is very important, always very important when you're
Safety first.
There's also wearing glasses. Yes. So Francisco will also film it, because the superconducting sample we have actually is not super big. So this is the YBCO. This is a cuprate, our high temperature superconductor. And we will now put it into this vessel and cool it down with liquid nitrogen.
Okay, so we're not professional videographers, so there's a non-zero.
You want to hold it because yes, we can.
So let's see if we can make this work so that everyone can see.
Okay, so Ruben's now pouring the liquid nitrogen. This is really cold. This is like 77 Kelvin cold. But as I was saying, you can also pour it over my hand. Nothing will happen actually. You want to do it? Okay. I was offering my hand to you. Okay. So, okay. And then what you can see here are two different magnets. So this one, maybe you can fill this up.
No.
So this one will produce an inhomogeneous field, and this one will produce a homogeneous or spherically symmetric homogeneous magnetic field. Okay. So maybe you want to test if it's really inhomogeneous. So Ruben will now check the polarity of these magnets.
This is attracting the pole of one, and this is the other.
Yes.
So they're differently polarized, alternating.
And then you can actually imagine how the magnetic field line would look like, and this creates an inhomogeneous field. Okay.
And this is homogeneous this way.
Yes, they are spherically symmetric. Okay. No. Yeah. So now Ruben will grab the sample.
Wait.
Is the
What happened?
wire?
I think it's the lack.
Is it?
Oh no.
I need your fingerprint.
Oh,
Thanks.
there we go. Okay.
So he will take the sample and first put it on top of the inhomogeneous segment.
We're just trying to build excitement.
There we go.
Oh.
So it's levitating. Can you actually confirm that by by putting something in between
Sheet
the
of paper.
magnet and the sample?
Oh,
Yeah, so it's really levitating.
But this is different from magic tricks. They also do this in the magic tricks.
It's kind of magic though. And now this thing is really locked. So the levitation comes from the Meissner effect, right? But the locking comes from the fact that we have these vortices in the superconductor. So maybe you can first try. Okay. No, please go ahead. Yes. So you can like put it upside down and it will not fall down.
Final project,
Hold
guys.
it
And you can also try to
hold
touch
it until it warms up.
what?
Oh,
Hold it until it warms up.
it'll take a while to warm up. This is
How long is it?
like a
Like
couple
10 minutes.
minutes.
But you can do it, it's fine
Okay, we'll do
actually.
it.
Try to touch it.
So,
So, see, it's really locked, huh? And can you also change the height?
That's expensive, I would say.
this is pretty cool. By higher?
Yeah,
No further down.
open the down. Yes, you can even like lock it in different levels. And it's still levitating, yeah. So maybe now you can put it on top of the, or in the homogeneous magnetic field.
Can tell that I'm not a videographer.
And it will still be locked in the height, because it's inhomogeneous in this direction, right? But it's homogeneous spherically, so we can turn it, and it will actually keep turning.
That's so cool.
Maybe you can turn it again.
Come on, turn it.
Yeah. It's refreshing for sure. Might lose a finger, but might lose a finger. Oh!
So what happened now is that the sample got too warm, and it lost its superconducting property. But we will cool it down again.
You understood what happened, just what happened.
It was
right?
too warm,
In that diagram, right?
Yeah.
The temperature increased, and then above it became normal conduction.
And I turn it. Yeah.
Wait, why does that spin? Right.
Thank you so much. We have some liquid nitrogen next, so you can try it yourself in the line of break.
And by the way, these demos and things are actually borrowed from the Harvard teaching labs. So in the courses there's
You should take physics at Harvard. Yeah. Because that makes sense. You should take physics at Harvard. Because it's cool.
Oh, what do you think? Should we go there, right? Yeah, okay. Actually, we have one more after that to show.
Discuss the demo.
The track.
Oh,
But it seems like she's given those, you said?
The glass I didn't get, but I have some.
Oh, she just borrowed.
So this is actually also pretty new for us because we're all theoretical physicists. So we usually don't do experiments. So it's kind of exciting. Okay. Oh, yeah. So here we also. Oh, not again.
I think you might be able to like go into settings and like make it like not
Not the right one, I need Okay, so here we build basically a small pneumatic track.
So this is how trains are going to work.
I can run it.
I don't think it's saving the recording, but
So we will pull down the magnets now with it as well.
wait, so are the like little track superconductors or just the
These are just normal
this
magnets.
is okay.
And now Ruben will put the superconductor on top.
So why do you need to cool the regular magnets when you,
Just works a bit better.
Yeah.
just, okay, alright.
So like so it doesn't warm up as much.
Because if the surface is not magnet, the surface is not cold, it will thermalize the
Just faster.
the superconductor faster.
Got it.
And then, yeah, so the problem we have is that we build it ourselves and it's not super homogeneous. So,
And also the sample is a little bit too large for the track.
so in principle, what you should see is that it slides above this magnet. But what you're now witnessing is the quantum locking again, because we did build a super
This is our failure, not
homogeneous track.
not of the world.
This is what happens when you buy something from Amazon. The track from Amazon.
Okay, so actually it's locked. So.
Get your superconductor.
But, I mean, in principle, you get the gist of it, right? So we have like a homogeneous track, and you can basically let the superconductor move around. Yeah. Yes. Actually, that's a good point. I mean, these superconductors are really small, so the magnetic field is not strong enough. But in principle, if you get a bigger one, you can put it first on top.
But that's like rectangle, but people are like not rectangles.
Wait, do you want to like put a person on the superconductor, or do you want to make the person superconductor? I would recommend this thing.
No, like, okay, so if I had like a magnetic bag and I wanted to have like magnetic shoes, so my shoes were the superconductors, how would you make that work?
So you can, I mean, maybe we can show this again. You can, we will use our big magnets again.
Stop. You're going to
And do we have,
She makes materials.
okay. And then you can just like put something on top. And it will still navigate. And you can put heavier things on top if you have a bigger superconductor. So like either we get you really big shoes.
That are very cool.
Like that.
very cool. Yeah.
When you want like superconducting trains, the idea is you just have your superconductors, and then you have like a layer of insulation, and then you have to like train forward, right?
Yeah, but the shoes are gonna be a little thinner than the train.
No, I'm not saying it's plausible for shoes, but
Like
like
now, is this like
That's all I love is
the new shoes that like superconducting?
online.
Yeah.
Like, how, what if like this field is going on, just has to walk, like, what do you do?
Oh, she was quantum locked and she went for the goal.
Like how big of an object you can put on top. This basically
Well, they like the magnets. This is like the and as a player, I'm just predicting often like jump down with the magnet.
If you guys can
So her lecture is not quite finished yet, so maybe you can repeat your question and she can then address to the whole class.
It was just like how heavy an object has to be to like bring the object down.
Yeah, I don't have a good answer to that. I would just try it out, honestly. But I've seen pictures where like really people are levitating and they're standing on top of a superconductor, which is maybe
Like a
1
really
meter in
nice
diameter. Yeah. That would have been a cool experiment, I agree. Sorry for that. Yeah.
So if you had something like a superconducting train or something, where is like the energy coming from that is making it more efficient than a non-super like just a normal train? Is the idea that we're losing less heat, or where or due to friction, or like what's making it more efficient?
So you can think of a superconductor as like a super strong magnet, which is really efficient because the currents, they can run without friction.
Okay.
And I think the main effect why these levitating trains, and I'll slide on that actually later, are so efficient is because they're levitating and there's no friction. Oh, there we go. Okay, so yeah, like one of the real world applications of superconductors are these levitating trains that are called maglev. So maglev comes from a combination of these two words, magnetic and
Hey
levitation.
guys, we are still presenting. Why are we having side conversations?
And yeah, like the speed record of the fastest train on Earth is pulled by a maglev train, which is 603 kilometers per hour, which I looked it up before, is around 380 miles per hour. So, can you? Oh yeah, here you can see some videos. I think this is not the fastest one, but you can already like see they are pretty fast. So how do they work? There are actually different types of maglev trains. The one that uses superconductors has this geometry, so we have these superconducting magnets on the train itself. And then on the side track, we have these levitation coils. So there are two like magnets, and the train actually levitates because of a combination of the repulsive force of these magnets and the attractive force between these magnets. And again, like these, basically think of a superconductor as a super efficient magnet.
Is there a reason why the polarity is switched from one side to the other?
I think this is because in the end you want to make them more stable.
Okay.
And you would actually accelerate them by switching the polarity of the upper magnet here.
Got it.
And then the train will get dragged along along this path, basically in the same speed as the switching of polarity. I guess you could like also make them symmetric, but I guess it's due to stability reasons.
But they alternate, so.
Yeah, you're right. In order to accelerate them, you can see that these tracked magnets, they actually alternate in polarity, and they drag along the superconducting train, or the train with the superconducting magnets, and accelerate them to much faster velocities than we saw here. Right. And okay, advantages, as you already pointed out, is that they're very, very efficient, energy efficient, because there's no friction anymore. There is, because it levitates, they can be super fast. They can also be smoother, again, because there's no friction. Currently, I think maglev trains are mostly used in Japan and China, because they're still pretty expensive, but there's research also done by other countries, also including the US. Right. Oh, so now let us very briefly talk about the theory behind superconductivity. And as I said already, it took almost 50 years to come up, for people to come up with a theory that explains superconductivity. And the first working microscopic theory was actually found or developed by Bardeen, Krugman, and Schrieffer, these three gentlemen here, and they also got a Nobel for that. So the core idea of this BCS theory is that two electrons, they can weakly bound together, and they can form something which is called a Cooper pair. And this Cooper pair is bosonic, which means it can condense. So condensation is the thing that Ruben explained already, and where you saw this cute video by Eric and Melba. So maybe let me very briefly remind you about what quantum condensation is. At very high temperature, it's totally fair, as we learned, to think about these Cooper pairs, or particles in general, as like billiard balls bouncing around with an average distance of, like, let's call it d. The lower the temperature, the more important becomes the quantum nature of these particles. And we should actually start thinking about them as waves. And these waves have also, these wave packets, they have also some characteristic size, which is given by the de Broglie wavelength, something we will also introduce. So at some point, if we even further cool it down, we can imagine that the extension of these wave packets become the same size as the interparticle distance here, and they start to overlap. And at this point, it really doesn't make sense to talk about individual particles anymore, but they will all fall into like the same quantum state, and we can describe that by a macroscopic wave function. And this is what is called quantum condensation. Here you can see a video of helium-4. Helium-4 is not a superconductor because there are actually no charges involved, but it can also condense. It's called a superfluid, and you can see it here. It flows without friction. So it will actually flow indefinitely because there's no friction anymore. I looped the video, so this is why you see this here indefinitely, but it will also flow indefinitely in real life. And this quantum condensation is the reason that there is no scattering possible, and that we have zero resistance in the superconductor. So this BCS theory turned out to be really successful because it can explain the two features we learned that a superconductor has, the zero resistance and also the Meissner effect. And it can also explain isotope effects, like why different elements have different critical temperatures. There are, however, some limitations. Like, for example, it's only valid for the conventional, so-called conventional or low temperature superconductors. And the high DC superconductors, like the YBCO sample we had, they are not described by the BCS theory. And actually understanding how the superconductivity comes, or where this comes from in these high DC superconductors, like for example the cuprates, is still something which people are working on actively. Like even here at Harvard, we have, yeah.
I'm still just a little bit confused about the Cooper pairs and how that explains how the condensation. I don't quite get how the Cooper pairs contribute there.
Okay, so I mean, the particles we have in the metal, or the free particles, are the electrons, right? But electrons cannot condense because electrons are fermions. And condensation basically means that all particles will occupy the same quantum state, the lowest energy quantum state. And this is something only bosons can do, but not fermions, because they are in the life-Pauli principle. So the electrons themselves, they cannot condense. But if we now pair up two electrons into a Cooper pair, this Cooper pair is actually bosonic, so this is that can condense. Yeah.
When the electrons are found, like how can they be found together?
Oh, that's an excellent question, yeah. So, intuitively, you would think, or you would exactly ask this question, right? They have the same charge. You're also spoiling my talk. So thank you very much for the question. There's the same charge here, so you would expect them to repel each other. The reason why they don't do it is because of these lattice vibrations of phonons. So think of a lattice. So we have the positively charged ion cores here. They are positively charged because they're missing some electrons, the electrons which can basically freely move around, right? And then we have the electrons which are negatively charged. So the electron now can move around this lattice and will attract the positively charged ion cores. And then it can move further around and further attract. So if we bring in a second electron now, this will basically see this like net positive regions in the solid and will get attracted by that. And it will follow the movement of the first electron. So you can think of them as weakly bound. And the reason why this actually works is that, it was a lot of work actually, so let's do that again. The reason why this works is that electrons are so much lighter than the ion cores, so they can actually move much faster. So the first electron left this position already, and it takes some time before the ion cores actually notice that it left already, and they will just take much longer to move back to their equilibrium position. The scale here is not very accurate. In real life, like Cooper pairs are much, much larger. So the lattice spacing here is 0.1 nanometers, and the size of a Cooper pair is like 1,000 to 10,000 times bigger than that. Right. So with this, let me actually summarize by giving you an overview of like all the Nobel Prizes involved in superconductivity. So the first one we've seen already, right? It was the initial discovery of superconductivity by Kamerlingh Onnes in 1911. And then 50 years later, almost 50 years later, the BCS theory was developed by Bernini, Cooper, and Schrieffer, and it was really the first macroscopic explanation of this conducting phenomenon based on Cooper pairing and like this collective quantum behavior. Then later, in the late 1980s, there was a third Nobel Prize, which was awarded for the discovery of the cuprates, so these high Tc superconductors. And again, YBCO is a cuprate. And this really sparked a lot of research in this direction, because like suddenly the critical temperature was increased by a lot, right? And still up to this point, like people are looking for new materials with even higher critical temperatures. I think with the overall goal to find like room temperature superconducting. Yeah?
For the Cooper pairs, why they have to be in pairs? Because like, couldn't you have like a link of electrons and they just keep going back and forth, like going across? Like, why does it only have to be a pair?
Like not an object of 3 bound electrons?
Yeah, because like, wouldn't they just be following each other, like in a line?
Yeah, okay, I mean like this is a kind of simplified picture.
Yeah.
But I guess what you're saying is right, but it's just like an effect in next order. So I guess it's easier to build a train out of 2 instead of 3 and 4 and 5 and so on. Yeah. And then also like 3 atoms would not be a boson anymore, right? So these like constructs of 3 electrons, sorry, would not be a boson anymore. So they couldn't condense. Yeah. And then there was another one, 2003, awarded to because of Ginzburg and Leggett for different things, including the theory for these type 2 superconductors, so the vortices, for the Ginzburg-Landau theory, which is in contrast to the BCS theory, a macroscopic phenomenological theory for superconductors, and also some related theoretical work in superfluidity and some microscopic quantum phenomena. But yeah, really the main takeaway messages from this talk should be that like superconductor has 2 defining features, right? First of all, zero resistance, and this is like was really surprising and still is surprising, right? That there exist these materials with zero electric resistance. And the second is the Meissner-Ochsenfeld effect, so that they are always field free. And right, the story of superconductors is not done. Still, experimental physicists are searching for new materials with superconducting features at higher critical temperatures, and also from the theory side, like these high temperature constraints are not really well understood. Yeah, thank you. Can I continue? I think so, yes.
So we're going to
What determines the
take a
temperature, like, of certain elements?
Yeah, so it's one way to think about it, like this.
Okay. And some.
Are there more questions?
I guess with the
there's a question of Francis.
This one.
And that's why.
So, yeah, so we're going to have, because of time, we're going to, because of the fact that there are two very good lectures coming up after lunch, and then you have to head back to get back to CRLS at 3. We'll take a short lunch break, so you will take your sandwiches, but I'm going to say one thing before you get your sandwiches, and then you can actually come here, and the lab technician will pour the liquid nitrogen, but you can actually do the experiment, and also with the fraction. Okay, so, but I want to leave one thing. In all of the lectures today, right, you saw one after another demonstration of a very profound ideas come to fruition, and not only that, win a Nobel Prize. So, in a way, it sort of gives a sense that 100 years ago, anybody who had any idea could end up winning the Nobel Prize. There is some truth to that. However, science evolves. Quantum mechanics now is far more diverse, far more complicated, complex science. So the ideas will take longer to develop and longer to realize and bring about the real science. So the time scale to a Nobel Prize may be longer. However, the nature of science has not changed. When we do an experiment, we do theory, and explain the physics, at the end, it turns out to be very simple. The process to get to the answer may be difficult, but when you describe something, it turns out to be, as you can see in all of these demonstrations of it, it's very simple concepts. But the actual thing is getting to it, is the part. So, I think, does it run? Yeah, sure.
The sound.
Is it? Oh.
Yeah, there's a huge. So this is the actual maglev facility near Fuji Mountain in Tokyo. I was there some years ago. So you can actually see the experimental maglev train right now. The day that I was there, it was clocking at 590 kilometers per hour.